This topic is hypothesis testing, and it's about finding out whether things have changed or things remaining the same. Here's an example. Over a long period of time, large fires occurred at the rate of 9 per year in the United States. But in 2012 there were 16 large fires. Does that mean that there's an increase in large fires, or was that number just by chance? In order to explore this, we need to identify a null hypothesis, an alternative hypothesis, decide whether we're going to use a one-tailed or two-tailed test, and look at a significance level. So the null hypothesis is the boring bit. It's the bit where you say, nah, things are just the same, nothing's changed. The alternative hypothesis is more exciting. Things have changed. Something's happening here. And what we do when we test hypotheses is we assume the null hypothesis is true, and then we find out whether the chance of the alternative hypothesis is greater than or less than the significance level. So this will be explained in more detail, but for the moment you need to make a note of these terms here: the null hypothesis, alternative hypothesis, one-tailed, two-tailed test, and the significance level. So we'll look at an example in a minute. We'll test a hypothesis, and we'll look to see if we get a value in the critical region. If the value we get is in the critical region, we'll reject the null hypothesis. And the critical value will be the first value you meet on entering the critical region. And the size or the significance level of a hypothesis test will be a probability. Normally 5%, sometimes 1%. But for the moment you need to make a note of these terms. So here's our example. We've got a variable which has a parameter of lambda, Poisson distribution with parameter lambda, and we'll say that the null hypothesis, the status quo, the boring bit, is that lambda is 10. Now, the alternative hypothesis is that lambda has changed, it's less than 10. So what we're going to do is we're going to test the null hypothesis at a 5% significance level. So what we're going to do to start off with is we're going to say x is in the Poisson distribution with parameter 10. And the null hypothesis, which is written h0, is that lambda equals 10. And we're going to assume that things are staying the same, and then we'll find what probabilities we can get to say there's been a change. Supposing we're going to test to see if lambda is actually smaller than 10. So h0 is the null hypothesis, that's how you write it, and h1 is the alternative hypothesis. And our level of significance is going to be 5%. So let's suppose that in a class there's normally 10 students late every week, so the rate is 10. And then it comes to nearer the exams, and the teacher decides that actually the punctuality is improved, and maybe it's fewer than 10. What evidence would convince us that lateness has improved? Let's suppose that we observe there's 3 people late during one particular week. What's the probability of there being 3 lates in 1 week? So we've got Poisson 10, here's 10. The probability of 3 people being late is 0.103. So let's consider that example. What is the probability that x is less than or equal to 3? X is less than or equal to 3, we can see from here, is 0.103. Sorry, 0.0103. So the probability of there being 3 people late in a week is around about 1%. So this is quite unlikely to happen if the rate of lateness is still 10. Now the word quite unlikely we can actually quantify. That's what the level of significance is. Anything less than 5% is considered very unlikely. It would be unusual, unlikely, not impossible, but very unlikely to get fewer than 3 people late if the rate was still 10. So if our parameter is still 10, here we are, 10, if on average we've got 10 people late each week, but in one particular week we get 3, then that's very unusual. It's less than 1%. And we're going to test, in this example, we're going to test at 5%. So it would be quite unusual. I've just picked 3 at random. What about the probability that x is less than or equal to 4? So the probability that x is less than or equal to 4, we can see here, is 0.0293. So that's still less than 5%. So if our parameter is still 10, the probability of getting fewer than 4 people late is still less than the significance level of 5%. So our null hypothesis is that things have stayed the same. It's still 10. Let's see what the probability is of these events happening. If we find there's fewer than 3 people late, that's very unlikely. Fewer than 4 people late, that's very unlikely. What about fewer than 5 people late? What's the probability that x is less than or equal to 5? Less than or equal to 5, we can see over here, is 0.0671. Now that's just more than 5%. So if we observed 5 people being late during this particular week, well, we could say that was quite possible, that might happen. The parameter is still 10, the probability of getting 5 is just over 5%. So fewer than 5 would not be that unusual, 4 would be unusual, and the cut-off point is the 5%. So what we can say from this is that the critical region is x is 0, 1, 2, 3 or 4, and the critical value, which if you remember that's the first value you come across when you enter the critical region, the critical value is 4. So what's this saying? We start off with the null hypothesis. We say the parameter is 10. If we observe 0, 1, 2, 3 or 4 happening, then the probability of getting 0, 1, 2, 3 or 4 is so small that we could reject the null hypothesis. Right, here's a similar example, but this time instead of testing that lambda is less than 10, we're looking at lambda being greater than 10. So it's a similar thing before. We always need to do this. We say x is in the Poisson distribution with parameter 10. Firstly state the null hypothesis. That's the boring bit, things stay the same, lambda is 10, no change. And then the exciting part is that lambda has increased, something's happened. And we're testing at 5%. So the significance level is 5%. So the thing is to find the critical region and to find what values we could observe that would make us think that the parameter has changed. Obviously very large numbers down here, very large numbers down here are going to make us think that the parameter has changed. The parameter is 10, so at some point down here we're going to say it was so unlikely we would observe these numbers here that the parameter must have changed. So let's pick a number at random, let's pick 20. What's the probability that x is greater than or equal to 20? Well, the probability that x is greater than or equal to 20 is 1 minus the probability that x is less than or equal to 19. So 19 we can see is here. So it's 1 minus 0.9965, which is 0.0035. So that's less than 1%. So if the parameter were still 10, the probability of seeing any number over 20 is really small. It's less than 1%. So if we were to observe 20 or more of these events, we would say that the probability of this happening is so unlikely that we would reject the null hypothesis. So notice that we're looking at 20, there's 20, but in fact we're looking at the 19 value because x greater than 20 is 1 minus it's less than 19. So let's pick another value at random. Let's say, what about 19? What's the probability of observing 19 or more? Well, that's obviously 1 minus the probability x is less than or equal to 18. X is 18, is here, 0.9928. Notice we're in the 10 column because that's the parameter. So 18 is 0.9928. 1 minus 0.9928 is 0.0072. So if we were to observe 19 or more, the probability is so small, less than 5%, less than our significance level, we would reject the null hypothesis. So we can carry on doing these examples. Greater than or equal to 18 works out to be 0.0143. Greater than or equal to 17 works out to be 0.0270. Remember, we're looking for 5%. 5% is the significance level. Probability that x is greater than or equal to 16. That's 1 minus the probability that x is less than or equal to 15. 15 is here, 0.9513. So 1 minus 0.9513, that's 0.0487. So that's nearly 5%. So almost certainly the next one is going to be what we're interested in, because we're trying to find a value where we get 5%. So greater than or equal to 15 is 1 minus the probability that x is less than or equal to 14. 14 is there, 0.9165. So 1 minus that is 0.0835. So what we've now got is that at 15, the probability of observing 15 or more is fairly high. It's more than 5%. But the probability that x is greater or equal to 16 is low. It's less than 5%, it's 4.8%. So that means our critical region is 16, 17, 18, 19, and so on. So I'm running out of room here, I'm going to squeeze this in. So the critical region is 16, 17, 18, and so on. And the critical value, that's the first one you come across, and that's 16. So don't squash your notes like this. That says critical value there. So this is very similar to the previous example, except that when you're finding greater or equal to 20, we've got to look for the row above at 19. When we're trying to find x greater or equal to 15, we look at the row above to be 14. So at 15, there's 15, we look at the row above because of this business here.